Hello everyone, welcome back to my channel. If you are new to my channel, please do subscribe and share to your friends. Today we are going to discuss one of the interesting topics in VLSI design, that is VLSI testing and testability. So it is one of the interesting topic and also it is one of the important topic in the VLSI design. So these are the contents: introduction, fault models, test vector generation, fault simulation and design for testability. These are the topics we are going to discuss under VLSI testing. Fine, in this particular session, I am just going to discuss the first three topics. Remaining two topics will be covered in part 2 video. Fine. So, let's see the introduction of VLSI testing. So, after fabrication of IC means integrated circuit, it must be verified. Fine, every IC must be verified after fabrication. So VLSI testing means checking the manufactured IC in order to verify its correctness. So in order to verify the correctness of a IC, we have to check the manufactured IC. So that is nothing but VLSI testing. So if the test results are satisfactory, then only that particular IC is qualified to be shipped to the customer. Otherwise, if test results are not satisfactory means, so again it will be sent back to the manufacturer. Fine. We have CMOS IC test. CMOS means complementary metal oxide semiconductor, which is a combination of both PMOS and NMOS. Fine. We have three types of CMOS IC tests. Those are functionality test, silicon debug test, manufacturing test. Functionality test is also called logic verification. So manufacturing test is also called gate level testing. So let's see the functionality test first. So functionality test means this test is actually verifies the functionality of a chip. It will just verify the functionality. That's it. It will just verify the functionality of a chip. So it is done by using a simulation. So by using some kind of a software, we are going to test the function of a particular IC. Fine. So silicon debug means. So silicon debug means it is actually used to find or detect the debugs. It is used to find the debugs on the chip. So it is very expensive when compared to functionality test. Why? Because here in silicon debug test, here the IC can be tested at a very full speed in a system. That's why the silicon debug test is a very expensive test when compared to functionality test. By next, manufacturing test. So it is also called gate level testing. So in this manufacturing test, so the test is conducted on each and every chip before shipping to customer. So in order to verify that silicon is completely intact or not. So that's why this manufacturing test is conducted on each and every chip by the manufacturer before shipping to the customer. So these are the different CMOS IC tests. So see here, the testing is done at several stages. So generally testing is performed at different levels. So the wafer level, packed level and system level, board level and feed level. So these are the different stages of testing. So initially the die is tested at wafer level. So initially the die is tested by using some kind of test vectors. We are going to test the die at wafer level. So observe here, it is called the wafer. A disc-like structure is there, no? So this disc-like structure is nothing but a wafer. So it is divided into number of segments. So each segment will represent one IC. So this segment only, this IC only. Fine. So this particular IC, so observe here, this particular IC will be packed like this. So it is just a plastic or ceramic package. That's it. Okay, all these are ICs only. Fine. So IC is also called die simply. So it is initially die is tested at the wafer level. So it is called the production test. So after that, after die is separated out from the wafer and packed and again tested with the same test vectors. So it is called final test or packed level test. So at the packing level, after the separation from the wafer, again we are going to test the die. So that stage is called the packed level testing. Fine. So next stage of testing is the board level testing. So at the customer end, the chip is placed. After separation from the wafer, the chip is placed in the board and here now the board is tested. So this test is called the board level test. Fine, next system level test. So if there are any malfunctions in the board level test, it will again send back to the manufacturer. So in system level test, board is placed in the system and checked if system works as specified or not. Fine. The last stage of testing is the field level testing. So when an end user tests the system while using a system. While so these are the different types of these are the different stages of the testing of an integrated circuit. Fine. So next concept is the fault model. So before discussing the definition of a fault model, let me tell you what is meant by fault initially. Fault is called is nothing but simply malfunction. So it is defined as the physical defect. So it is the physical defect of one or more components or the connections between the components in the given circuit. So fault means it is just a physical defect in a given circuit. Okay. So this is all about fault. So now come to fault model. So a model for how fault occur and the impact on circuit is called fault model. So we have two popular fault models. Those are stuck faults, stuck open or stuck short faults. So these are the two popular fault models we have. Stuck fault means in stuck fault we have stuck 0 fault and again we have stuck 1 fault. These are the stuck faults. Fine. So initially we are going to discuss stuck faults. So initially these stuck faults will assign a fixed value. The fixed value may be either 0 or 1. Fixed value means either 0 or 1 to a signal line in the given circuit. Fine. So fault models, these fault models can be detected by using the basic gates. Basic gates means AND gate, OR gate, also inverter, tri-state buffer, all these are the basic gates. Right. So see here, stuck faults. So already I had said now we have two types of stuck faults. Those are stuck 0 fault and stuck 1 fault. So let's see what is meant by stuck 0 and stuck 1 fault. So when the signal line always present at logic 0 is referred as a stuck fault. So observe this particular diagram. Here we have the AND gate. We have two terminals A and B. Here the B terminal is hanged to stuck 0. Then we can observe the output is stuck to logic 0 only. Output is stuck to logic 0 only. So this is called the stuck fault. Okay. So in the similar manner, when the signal line always present at logic 1, so it is referred as stuck 1 fault. So observe here I am considering one simple OR gate. So in simple OR gate we have two terminals A and B. So observe here, this A terminal will be hanged to stuck 1. Okay, this A terminal will be hanged to stuck 1. Therefore we can observe the output is always stuck to logic 1 only. So this is about stuck 0 fault and stuck 1 fault. Fine. So see, let us see the example in order to get a more clarity on stuck 0 and stuck 1 faults. So observe here I am considering one simple XOR circuit which has 12 fault sites. In these 12 fault sites we have stuck 0. So and we have stuck 1 also. That means stuck 0 faults are 12. Stuck 1 faults are 12. So totally we have 24 single stuck faults. So we can observe, so we can identify, we can detect in this particular XOR circuit we have 12 faulty sites. So see here the 12 faulty sites are at different nodes A, B, C, D and so on up to K. Fine. So if I am giving the test vector simply remember that test vector means input only. Okay, if I am going to give the input is 1 0 for this particular circuit, so actually we are going to get 1. So if I am going to give the test vector 1 0 for this following circuit, so if there is no any fault, if there is, so it is a good circuit. If there is no any fault in this particular circuit, we can get the output is 1. So if there is a stuck 0 fault at a node H, so if there is a stuck 0 fault at node H, we can observe 0 in the output. So observe here, initially if there is no fault we can get 1. So if there is a fault, the output is changed to 0. That means, so for faulty circuit value output is 0, for good circuit value the output is 1. That means if there is stuck at 0 and stuck at 1 faults, the output will differ. So according to the input combination. Fine. So let's see the stuck open or stuck short fault. So what are these faults? So these are called the transistor faults. Simply these called as transistor faults. Actually the MOS transistor is considered as an ideal switch. So always remember guys, so MOS transistor will act as an ideal switch. It performs on and off action with respect to the gate terminal. Here the gate terminal is acts like a control input. According to gate terminal, the MOS transistor performs on and off action. That's why it is called ideal switch. So and two types of faults are modeled in MOS transistor. Those are called stuck open and stuck short. Okay, in stuck open, a single transistor is permanently in the open state. Permanently in open state, whereas in stuck short fault, single transistor is permanently in the shorted stage. Okay, irrespective of its gate voltage, it is permanently shorted stage. Okay. So let's see the stuck open fault model. So it is the stuck open fault model. Here I am considering, so it is the circuit diagram of the CMOS NOR gate. CMOS NOR gate, which is the combination of both the PMOS and NMOS. So actually, so this part is called the pull up network. So actually it is called the pull up network. So this part is called the pull down network. So in pull up network, we have the two PMOS transistors are connected in series. In pull down network, two NMOS transistors are connected in a parallel. So totally it is simply, remember guys, simply the circuit diagram is a NOR gate only. So simply it is a NOR gate. Fine. So it is CMOS NOR gate. So observe here. So if the test for stuck at 0, so if I am going to give the input for this circuit for CMOS NOR gate, if I am going to give the input 1 0. So if I am going to give the 1 0 for the test for the stuck at 0 part, so we can actually going to get the value is 0 for this circuit. So if I am going to give 1 0 for this circuit, what will happen? 1 plus 0, 1 bar means 0. That means if I am going to give 1 0 as the input, we can get the output is 0 if there is no fault in this particular CMOS NOR gate. Okay. So if I change the input, so if I am going to give 0 0 as the input, 0 0 0 plus 0 0 plus 0 whole bar, that means 1. So if there is no any fault in the CMOS NOR gate, if I consider the input 0 0, I am going to get the output is 1. Fine. But if this PMOS transistor will in stuck open stage, so we can get the another input. So that is Z. It is indeterminate. It is different from 0 or 1. Okay, it is completely different. Okay, we can get another output that is completely different. That means here 0 and 1 are the good circuit state, whereas Z is a faulty circuit state. That means so it is Z is a undetermined stage. So we don't know what is this output, whether it is 0 or 1, we don't know. So when will we going to get the Z? When this particular transistor will be in open state. So when this particular transistor will be in open state, then only we can get undetermined stage. See, if it is not in open state, so if there is no fault, we can get the good circuit values. Those are 0 and 1. Fine. So next, stuck short fault model. So in this fault model, if I am going to give, so same thing guys, so it is also simply a NOR gate. It is also a CMOS NOR gate. So with PMOS transistor connected in series and NMOS transistor connected in parallel. So if I am going to give the input 1 0. So if I am going to give the input 1 0, the output will be 0 only. If there is no fault, So if there is no fault, I am going to get the output is 0 point. So if there is a stuck short at this particular transistor, I am going to get the output as X. It is also undetermined output. So here the 0 is the good circuit value, whereas this X is the faulty circuit value. It is undetermined state. We don't know whether it is 0 or 1, we don't know. It is the undetermined value. If there is a fault in this particular circuit, if there is no fault, we can get 0. So here from VDD to, from this particular VDD to ground, one current is flowing. That current is called IDDQ. So it is also called the quiescent path. This current will flows from this VDD to ground. Right. So see here. So next one, test vectors generation. So before that, let's see the test. What is meant by the test vector? So the test vector means the input combination in which presence of fault produces an output that is different from the fault free output is known as the test vector. So simply the test vector means the input combination which yields different output rather than the fault free output if there is a fault. So see here, observe here. So observe here. So here I am giving the input that is 1 0. So if there is no fault, we can get the 0. Fine. So if there is a fault, we can get another output that is different from the previous output. We can get another output is X. So if there is a fault, so then this 1 0 is called as test vector. Right. Okay. So that's why here the input combination which yields different output rather than the fault free output. If there is a fault in the particular circuit is nothing but a test vector. Here the generation of test vector is one of the complicated process. Okay, for that we are going to issue or we are going to formulate one new method. We are going to illustrate one new method that is called the fault table method. By using this method, we can easily generate the test vectors. Generation of test vector is one of the difficult tasks in the testing process. So see here, let us consider the fault table method. So I am initially consider the circuit consisting of an AND gate and OR gate. Okay, so this is the circuit which consists of AND gate and OR gate. Here the C equal to A into B. So this output Z is equal to simply C plus T, whereas Z equal to AB plus T. So it is the output for the Z. Okay. So observe here. So this is the circuit consists. It is built with by using AND and OR gates. So it is a set of all possible single stacked fault model. Here I am having the 3 input combination, that is X1 bar, X2 and X3. This X1 is inverted here. That means here X1 bar we are going to consider. Okay. So for 3 input combination, totally we can obtain 8 outputs. Totally we can get the 8 combination. It is 1, 2, 3, 4, 5, 6, 7, 8. For 3 inputs, totally we can obtain the 8 combinations. So it is a fault free output Z. So 0, 0, 1. So let us consider this particular input 0, 0, 1. So X1 is 0. 0 means it is inverted now 1. So another X2 is 0. Okay, 0. So next X3 is 1. Okay, 1 into 0. So we have to perform the AND operation. 1 AND with 0. That is 0. 0 OR with 1. That is 1. Okay, it is a fault free output. Okay, if there is no fault in circuit, actually, so this is a conventional output. Okay, if there is no fault in this circuit, we can get all these outputs. So it is a fault free output Z. So if there is a stacked fault, so if it is a stacked 0 fault, so if it is a stacked 1 fault, so if it is a stacked 0 fault at A, B, C, D, we can get A0, B0, C0, D0. So A0 means stacked 0 fault at A node, B0 means stacked 0 fault at B node, C0 means stacked 0 fault at C, like that. So similarly A1 means stacked 1 fault at A, stacked 1 fault at B, stacked 1 fault at C, and stacked 1 fault at D respectively. So all these are the different stacked 0 faults and stacked 1 faults. So already I had explained what is stacked 0 and stacked 1 fault. So all these are the faulty outputs. So it is the fault free output. So these are the faulty outputs. So that stacked 0 fault outputs and stacked 1 faults output. So now we are going to consider the fault cover table. From this particular table we can obtain the fault cover table which can easily generate the test vectors. So observe here. So it is the circuit. It is the table what we have obtained previously. So it is the fault free output, this column. So it is the faulty outputs. Fine. So these are the test vectors. So already I had given the definition for test vector. So these are the test vectors, means simply input combination x1, x2, x3. So observe here. So all this for this 0 0 0 0 1 0 1 0 1 0 1 0 1 1 1 0 and 1 1. So see here. So if there is a fault A0, B0 and C0, that means stuck at 0 fault at A, B, C. Okay. So observe 0 1 0 0 1 0 combination. So 0 1 0 combination. So if there is no fault, we can get the what we are going to get 1. So if there is a stuck at 0 fault, so what we can obtain at the node A, B, C, observe here 0 0 0. Observe here, this output is different from these outputs. Okay, this is different. So we have to put one cross mark here. So remaining all are same only. Okay, for 0 0 0. So here it is 0. Here all are 0. Here 1. Here A0, B0, C all are 1 only. So here 1. These are. So only this combination will change. Okay, only this combination will change. That's why we have to put one cross mark. So this 0 1 0 now we can call it as test vector. Okay, this 0 1 0 will called as a test vector. So why? Because the fault free output and faulty outputs are changed with respect to input combination. So that's why this 0 1 0 will called as a test vector. Okay, so observe D0. Okay, it's over. So observe D0. So observe here D0. So if there is observe the combination, the input combination 0 0 1. So for 0 0 1 for D0. So if there is no fault, what we can get the output 1. So if there is a fault, so observe here for D0 we can obtain 0. So this 1 is different from this output. So that's why we have to put one cross mark. So observe 1 0 1 1 0 1 combination 1 0 1 combination. So observe fault free output 1. Observe faulty output it D0 0. So this is also different. So this is also different. That's why we have to put another cross mark here. This 1 0 1. Now we can call it as it is also called test vector. So observe 1 1 1 1 1 1. We can get 1 here. So we can obtain 0 here. So this is different from this. So that's why this 1 1 1 is also called as a test vector. We have to put one cross mark here. So D0 is also over. So observe A1. So for 1 1 0 for 1 1 0. So stuck at 1 fault at A. So for 1 1 0 for 1 1 0 a fault free output is 0. So observe A1. Faulty output is 1. So fault free output is 0. Faulty output is 1. So this is different from this. So that's why we have to put one cross mark here. In this way we can apply all these cross marks like that only. So all these 0 0 0 0 1 all these input combinations are called test vectors. So what exactly the test vector means? The input combination which yields different output is rather than the fault free output if there is a fault. So if the previous output and current output are changed according to input combination, then that particular input combination will be referred as test vector simply. Thank you.